Ron Hawkins, Director of Industry Relations at SDSC. And I think good days are in order. Looking at the registration list, I didn't see anyone coming in from east of the East Coast, but if I missed you and the sun's not shining where you are, good evening. But for those of you who have joined us before, welcome back. And for those who are just joining us for the first time, we hope you enjoy this, and we hope you make it a regular part of your work life. But today we have an encore performance from GigaIO. I think they joined us a couple of years ago, and this is a company that's really been in it for the long game, in the fullness of time, as we've seen the emergence of greater reliance on heterogeneous computing. We've seen the GPUs emerge as the kind of the workhorse for AI and machine learning, and even some HPC simulation workloads. We've seen the rise of application-specific accelerators like FPGAs, and the new crop of deep learning and neural network chips, and this need for disaggregation and composability in large-scale computing environments has really become evident. So this is a company that had a vision. They kind of saw the future, and they've as I've said, played the long game and brought this technology to market. So it's really a great story for San Diego startup. And we've got Alan Benjamin, the CEO, here today to give us an update on the technology and the product and the application. So without further ado, I will hand it off to Alan.
Excellent. Thank you so much, Ron. And obviously all the work that we've done with San Diego Supercomputing over the years has been invaluable to us. And we really thank you for inviting us to give this presentation and update today, because you're right. It's over the last several years, trends have really moved in the direction where the obviousness of needing a fabric-based computing is becoming quite evident. So I'm going to share some things about what our network does and why we do what we do. And then towards the back end, we'll talk about some data, right? And we'll show, what is it that, people have, issues in terms of, oh, geez, am I going to lose performance if I do this? And in fact, we're going to show you it's just the opposite, that, your flexibility goes up, your performance goes up. So, Ron alluded to why heterogeneous computing. So we'll just start with that as a course. Moore's law, and these slides are from NVIDIA. And now obviously they have a lot of interest in showing that Moore's law has actually run its course. Intel slides look a little different, but at the end of the day, nobody really disputes the fact that CPUs in and of themselves alone do not drive performance any longer. And it's more of an architectural question. And heterogeneous compute really does help tremendously in terms of performance. And with NVIDIA's help and AMD's help, and now Intel is really into this, the number of applications now that can take advantage of GPUs and other kinds of accelerators has really exploded. And so, it was interesting. I looked at this data. 5 years ago, this number was less than 300, and it's this is a couple of months old data now at 1,800, and we're probably up to 2,000. I mean, the pace at which applications are being modified to take advantage of GPUs is really accelerated. And by the way, that's one of the issues, and we'll talk about that. So, the reality is, once you start to take advantage of different kinds of accelerators, the accelerator is going to take a particular math library or a math function and is going to accelerate it. Well, once you start down the path of, I can use an accelerator to enhance the performance of a particular aspect of a program, why not use, you can pick multiple libraries that in fact can get accelerated. And so once you go down the path of heterogeneous, ideally you want to be able to take advantage of a lot of different compute capabilities. And, we talk about GPUs, but it could be multiple kinds of GPUs. It could be FPGAs. Ron talked about, new ASICs. I know a couple months back, the NEC folks did a presentation in the same forum talking about their vector processor unit. So, we can take advantage of any and all ideally once you start down the path of, look, I want to put the computation where it's best run. And even though today we're going to do a lot of talking around the compute side, the storage side is the same. And so whether or not you want to use NVMe drives or even rotating media or Optane, Intel Optane storage or Intel Optane persistent memory or even memory itself, in the ideal world, all of this should be part of the mix and you should be able to do that. Question would be, do you actually have an interconnect capability to tie it all together? And that's exactly why we're here today to talk about it. So the challenges, for the IT organizations, whether it's, San Diego Supercomputer or, the enterprises, it's really an interesting time for these folks because the challenges are not small, right? On one hand, it's just a simple fact. The refresh cycle on servers just does not match the innovation cycle on GPUs. And we have heard from so many people that they buy a server, they want to put it on a 3 to 5, maybe even a 7-year depreciation schedule. But oh, by the way, the GPU or the FPGAs, they want to refresh every 18 to 24 months. And so there's this, if you've taken that GPU and you've put it inside the server, you're either writing off the server well before they would like to, or they're having to hold on to these accelerators. So these things just simply do not match, and people want to change. The workloads are diversifying and they're expanding. And we'll talk about, some of the use cases here in a second. But suffice it to say that as applications are starting to add in accelerators, they're all getting, shall we say, better. And better is a relative term. People they're making their applications faster, or they're making them more accurate, or they're adding in the capability to add more elements in. So all of the workloads are expanding. And at the same time, most of the organizations are being asked to take in a very different new kind of workload of artificial intelligence and data analytics. And those workflows look quite different, but the infrastructure looks similar to what the scientific computing is doing. And so they're being asked to take on these workloads. And the hardware itself is diversifying and expanding, right? We saw on the last page, the GPU, there's more GPUs, there's more FPGAs, they're becoming more specialized. And so you've got new workload expanding. And so, but at the end of the day, the budgets aren't increasing. And so people have to be able to do more with the hardware that they've got. And, we've seen from a number of studies, you take a GPU and you stick it inside of a fixed infrastructure server, and on average, it gets used 15% of the time. And so for most organizations, they simply can't afford to buy really expensive devices and have them use so little. So how do you get more out of the infrastructure? So here's an example. We talked to a number of companies. This is an automotive company. And they would say, look, at the end of the day, we've got half a dozen to a dozen applications that our folks use all the time. And, we wrote down the ones that they are using. Every one of these 7 are going through change. They're all adding capabilities to add in GPUs and FPGAs. But as you would expect, every one of these applications, they are lumpy in what they require, right? Some want more memory, some want higher IO traffic, some of them want more GPUs, some of them want a couple of stages of GPUs. So they're all lumpy, And as they would say, they're getting lumpier. And of course, the lumps don't add up. And the way that CATIA needs to evolve is different than ANSYS Fluent. And so, the question here becomes, there's really some difficult choices that, the folks that run the systems now have to make. And so they either are facing the challenge of having to build multiple infrastructures. So take that last 7, they either go down the path of building 7 different infrastructures, right? Or they build a single infrastructure, they optimize it for one, and they make it suboptimal for everything else. And in the end of the day, that sub-optimization can be really quite dramatic. So this one doesn't seem to be very appealing for many people, right? Because you got one group that's really happy and you got 6 groups that are really unhappy. And so what if it's possible to be able to really dynamically be able to change the infrastructure so that you can satisfy the need for growth in all of these and pick up that new AI workload? And so we believe, at the end of the day, fabric computing is in fact the key to making this happen. But there's some characteristics that have to be part of this solution if it's going to be successful. And, number one, it has to deliver full performance. And we heard from a number of folks early on, and there was a quote that one of them gave us that was really has driven what we've done. And they said, look, everything about disaggregation is fantastic, right? It delivers everything that we need, but I can't disaggregate unless I can re-aggregate again without getting killed in performance. And so the solution, the optimum solution here has to have full performance. It's got to have great bandwidth. It's got to have great latency. It's got to have both. It's got to work with any workload, right? We talked about, once people go down this path, NVIDIA GPUs are fantastic, but they make a whole bunch of them. And oh, by the way, it's not just AMD's GPUs. If you're doing double precision floating point, they're really very impressive now. Or Xilinx make some great FPGAs. So I mean, it's got to be able to work with any of the workloads and any of the components. It's got to be based on open standards because you just simply don't want to be locked in. And unfortunately, in this environment, an awful lot of people have gone down the vendor lock-in path, the walled garden approach. And we as a company feel that it has to be open, else it's the wrong approach. You want to be able to scale these systems, and it's not just scale them up. You want to be able to scale them down to the component level. If this workload needs X number of GPUs or FPGAs, you want to be able to put them together on the fly, run the job, and do something else, right? It should be able to use my existing infrastructure. You may have a bunch of servers that you say, look, I'd really like to add a GPU or two to easily, but also I want to be able to include some new servers, for example. So I may have, a couple of racks of, existing, Skylake Intel servers, but oh, by the way, I want to add in some of the newer Ice Lakes, or I want to add in some of the AMD-based servers, or maybe even the ARM-based servers. So I want to be able to use all my existing infrastructure, but I also have to be able to easily accommodate new things. And at the end of the day, God, we've heard this 1,000 times, please, this has to be easy to deploy. It can't become more hassle. My IT staff has to be very capable of doing this. And ideally, I use my existing tools. I'm using Slurm, I'm using Bright, I'm using, Control IQ, I'm using whatever. Please let me use my existing tools to manage this also. And so what we have created is what we call fabrics, right? It's a universal dynamic fabric, and it is the only routable, and we underline the term because it's a really important term for us. It's the routable PCI, and in the future, CXL, right throughout the rack. And it does what we've talked about. It'll work with any workload, any component. It's based upon open standards. Gosh, I mean, we have thrown dozens of devices into some of our resource boxes, and I don't think we've run into one that simply does not work. If they conform to the PCI spec, it just works. And it runs at full performance, right? We have generation 3, we have generation 4. And at Gen 4, PCI Gen 4 speeds, we have things running at 256 gigabits, and it's really quite something to see, right? Because of the fact that we're routable, we scale really well. And we'll talk about this because we handle server to server communication in addition to simply server to resources. And at the heart of the matter, the difference between what we do in this dynamic fabric is that we are, at the heart, PCI Express is in fact a data-centric network. It is not a store and forward. So you're not storing data, you're not, putting in bounce buffers. And so it inherently reduces latency and improves the security profile of the cluster. And as I said, we'll talk about this in the context of compute elements, but it could very easily be storage as well. I mean, inherently, as you understand more about the fabric system, it really doesn't matter what the endpoints are, right? And we're very easy to move information from one GPU to an FPGA, for example, or from storage into an accelerator. And so we're just going to talk about this largely in terms of acceleration and compute today, but it is also storage and memory as well. So most infrastructure today is put together, it's a static architecture. It is a rack full of servers that's connected either with InfiniBand or with Ethernet. Maybe it's Rocky, maybe it's not. And you have a certain number of servers. In this case, this was Ron's configuration. And which is very common. It's a very typical configuration, 4 GPUs per server, rack full of servers. And if you need to run a job, you put it on a server. So if you've got a job that's going to need 1 GPU or 3 GPUs or 4 GPUs, it goes on one of the servers and it's going to run. And if you need 2, the other 2 are sitting there doing absolutely nothing. And if you need more than 4 servers, you run it on more than one server. And the communication between the two, if in the case of, if these are NVIDIA GPUs, it's a construct called GPU Direct RDMA. And we'll show you the performance penalty that you pay, right? If you got to run a job here on 8 GPUs, there's quite a bit of performance that is lost when you communicate between these two. Now in the future, we think it goes this way. Right, so the fabric system becomes the new top of rack switch, and we have resource boxes here where we will pull the GPUs out of the servers, and they now become part of a resource box. There's no servers in these boxes, right? I mean, they are simply a set of resources that are now available to anything in the network, and the servers consequently become much simpler. So all of the heating and cooling and all those sorts of requirements come out of the servers. They become much simpler again. They go back to being, in most cases, 1U units. And oh, by the way, because we route PCI, we still do all the connections between the servers. So if you're running MPI jobs, for example, or anything that requires TCP/IP or NVMe over Fabrics or whatever, it runs natively on Fabrics. So the servers now can access any of the GPUs and anything that's in the system. So real simply, this is the simple composition and resource sharing. You've got a job, you've got a handful of servers. One server grabs, 8 GPUs. The next server needs to have 4. You're setting this up through, the software that you're used to. So if you're running Slurm, you submit your Slurm job exactly the way you've always submitted your Slurm job. And we have worked with outside vendors now that have the Slurm plugin that will recognize the resources being requested and will compose this on the fly. Or if you're using OpenStack or Kubernetes or Singularity containers and Control IQ software or Bright Computing or whatever software that you want to run, we can run with. And the job changes. You finish that one job, you reconfigure, and you run a different job, and this can go on all day long. And you're reconfiguring this network as your jobs progress. and you're taking advantage of all the various accelerators that you have. We could continue to play that game, ad infinitum. People ask me all the time, does it actually work? And I'll tell you, we of course use our own tools in our system, and our development engineers and our QA engineers are, quite desirous of the resources. And, being a smaller company, we can't afford to get everybody all the resources that they want at their own disposal to be used at 15% utilization. And so we did some measuring on the number of times we make changes a day to our infrastructure. We've got 2 racks of gear, and we make almost 200 system changes a day. Nobody touches a thing, right? It's all done via the software. It's all cabled up. We will physically reconfigure our equipment about 200 times a day. And I get it, right? That's extreme in terms of, the sort of changes that people want to make, but it works, and we've been doing it for quite some time now. So, one of the other benefits here is it gives you a lot of different flexibility. So we've shown that, we were using one kind of accelerator. Well, there's nothing to say that in these resource boxes, you can't have, some GPUs that are really quite good at, let's say high precision floating point. And maybe you then want to run some different types of accelerators for inferencing. And maybe you want to add in some FPGAs, and you want to add in something that can do the visualization parts of your workloads. And so you're not tied to a particular kind of accelerator in these boxes. And it's very easy to add resources as you grow. And so, you don't have to add large slugs of racks of equipment or whatnot. You need to add a handful of GPUs into your system to improve performance. You add a couple of GPUs. It's very easy to add and upgrade and change as you go. And because these boxes from us are actually 10 slot devices, you can also add, for example, Intel Optane drives directly into the box and have really fast access to scratch memory, for example. And at the end of the day, increasingly people want to let the workflow drive the composition of a particular server or of a cluster, right? So, let the workflow is going to be optimal across a couple of devices. And I'm going to show you an example here of a moment at work we did with SDSC, where we did exactly this, and we got really some dramatic results from being able to let the workflow configure the system to match the workflow, not the other way around. And, one of the things, because of the fact that we do server to server, and I said we were going to concentrate on, the compute side of things, there are times when you would like to have large pools of these accelerators working together. And this is often quite difficult to do. So in this particular case, there's 16 GPUs. There's very few servers on the market that can actually handle 16 GPUs. And it's going to be a relatively newer server that can even handle 8. And so in this case, we're running a nickel ring, an NVIDIA nickel ring across all 16 GPUs. And oh, by the way, we've extended a nickel ring now out to 32 GPUs, which is really kind of interesting because very few people can do it, we've been told. And so whether or not you're running this on, if you've got 2 servers that can handle 8 GPUs each, or maybe you've got some older servers that you would really like to continue to get more benefit from, and they can only handle 2 or 4 GPUs, guess what? You can still pool these together, because across Fabrics, we can run that GPU direct RDMA across the various servers and still give you a large pool, even if the servers themselves can't handle it. So now let's talk about some of the performance tests. So you might say, geez, this is really great. I can disaggregate, I can reaggregate, but what happens on the performance side? And so we're going to show you what now comes. On the GPU side, we're going to talk about comparing what we will call converged, and that's when you put a GPU inside of a server, one or more. So what happens when we put GPUs inside of a server? What happens when we compose GPUs to servers? So we put them in that resource box and through the Fabrics network, attach them to a server. What happens when we run GPU direct RDMA across multiple servers? And then I'll show you a case on scaling out to larger sizes of numbers of GPUs. And then I'm going to show you the work that we have done with San Diego Supercomputer that sort of brings that all together. All right, so test number one and data is converged versus composed. Converged, in this case, we took 8 GPUs and stuck them inside of a server. And so, you know, it was one of the big servers, in this case, the Supermicro Big Twin. We added 8 GPUs. This particular server, 4 GPUs are attached to a particular processor, 4 to the other processor. And so communication, if you're going from one side to the other, goes through the UPI bridge. Everything else can communicate GPU to GPU. One benefit of being able to compose GPUs, so we took all 8 GPUs and stuck them inside our resource appliance. They will all talk to each other directly across our network. And I'll show you, if you have multiple boxes, right, it never has to come back to the compute node, and that has a large impact on performance. So here's composed versus converged, and you can see the results are the same. So so this is one GPU, whether you put it inside the server or whether you compose it to the server has no impact on performance. And in fact, when you got to the 8, the composed, right, being in that resource box, actually runs significantly faster than having them inside the server. So architecturally, whether you put them in the server or whether you compose them will have little impact. And in fact, it may be beneficial depending upon the server itself. So now let's look at what happens if you run a job where you have the GPUs effectively inside a server. In this case, we took all 8, we composed them to a server, right? Ran what NVIDIA calls GPU direct, the ability for GPUs to talk to themselves within the box. And we compared it to running RDMA, right? So we have 2 compute nodes where we've composed GPUs. So effectively, we have the same 8 GPUs, and you can think of it as 4 GPUs in this server, 4 GPUs in this server, and we're going to run the job across the entire construct. And in this case, instead of running a GPU direct over InfiniBand or over Ethernet, we're running it over Fabrics. And this one probably will surprise you, right? Because the results would show, and let me explain this real quick. We have 2 tests here. We have ResNet 50 and we have inception testing. And the blue bars in each case are the number of GPUs that are in one server. So this is 8 GPUs sitting inside of one server. The yellow bars are the same number of GPUs, just split up between 2 different servers. So in this case, this is 4 GPUs in 2 servers for a total of 8, as compared to having 8 GPUs in one server. And so you can see, which is, and I'm going to show you the data from San Diego Super in a second. This is quite surprising to most people, because in normal cases, if you have to communicate across 2 different servers, you lose some considerable performance. And in our case, running this across Fabrics, it simply doesn't matter. So whether you have 2 GPUs composed to a server, which was the same as 2 GPUs sitting inside the server, or you put 1 in each, right, you're going to get the same numbers. So if you're trying to revitalize older servers, this is a great construct now. So you can easily add GPUs to older servers, and when you need to do larger jobs, you can still run that job across multiple servers. And it is interesting to note, once again, when you get out to larger numbers, in this case, we're actually running faster when we've split the jobs up. And I will say this becomes heavily dependent upon the software. We have other cases where this will be slightly less performant. In the ResNet inception testing, you can see it actually does better to split across multiple servers because the GPU is much more efficient in the compute. The CPU still does it. And so having more CPUs still actually helps the result. And then in terms of scaling, for fun, we took a case where we took 32 GPUs and we put them into various, we put them into the resource boxes, attached it to a compute node, and we're successful in getting this construct to run well. And as you can see, it scales, the performance factor across Fabric scales really well. And whether we were doing this, in this case, this was one compute node with 32 GPUs, or from the last chart, you could see if we split this up and put 8 and 4 different servers, you're going to get pretty much the same results here. So your ability to scale out when you need larger numbers of GPUs is going to work really well. So now let's talk about the San Diego use cases. We've done with Ron's help, we've done some really nice work. This one was done about 18 months ago now, and it's really germane to the topic. So one of the applications that they run there is a seismic simulation package called AWP. And Ron initially gave us the mandate. He said, the existing setup runs pretty well. Is there a way to match that performance but for less money? And so it was a pretty interesting challenge. And I'll tell you up front, we did not succeed in his challenge because at the end of the day, we could not match the performance. We actually kept getting higher performance. So I'll just sort of lead with that, right? We kept getting, and at the end of the day, we delivered 25% higher performance for about a third of the cost. So we'll come back to this one. Let me show you the test setup that it was. The existing system was very similar to what we talked earlier. They have an InfiniBand switch. They had four servers that they were using with 4 GPUs each. And initially, our system looked very similar to this setup. And as the researcher, in this case is a gentleman by the name of Dawei Mu, was working on the system, he started to realize that he didn't necessarily have to mirror the same setup. And at the end of the day, this was the final configuration. It was actually, he went from 4 servers to 1 server, where we started with 4. And he was actually attaching all the GPUs to a single server, and he added storage directly into the network. So now to come back, we ended up with 25% higher performance. So their existing system is, the Comet system there is, you can tell this is a couple years old now. They were running P100s at the time, which then were $6,500 a piece. We were running 1080 Ti's. We were a brand new startup company. We couldn't afford the P100s. The 1080 Ti's obviously are not there any longer. And they were at the time about $1,000 a piece. So on the performance scale, what is it that the P100s got you? Well, lower is better on this chart. And so if you were running this on 1 GPU, you can see the P100 is about 50% faster, right, as an individual GPU. So that's what your $5,500 bought you for GPU cost differential. However, once you got to 4 GPUs, we had actually caught up in performance. And remember now, this is $4,000 worth of GPUs that are now running at the same performance as $26,000 worth of GPUs. And when you got out to 8 GPUs, we're actually running faster, considerably faster. And remember, this is $8,000 of GPUs against over $50,000 worth of GPUs in Comet. And so, and what's happening here is the utilization of the GPUs. And this is that performance penalty. I talked about the penalty that you pay for GPU direct across the networks as they exist, the legacy networks, you can see the utilization of the GPUs drops dramatically. Meantime, in fabrics, it's still chugging along well into the mid 90s. And so even though they're a less powerful GPU, the fact that they're fully utilized, fully stocked with memory, keeps them moving right along. Now, that study then got Dawei thinking, and he actually proposed this process, and this is back to letting the workflow decide the configuration. And so it turns out in the work that they do, they actually have a two-step process. So they're getting the data in from the field. Step number one is to do the computation on all the field measures. So they can actually do the computation on the seismic waves themselves. And step number two then is to take the output of the computation and run a visualization so they can watch this seismic wave roll down the hillside. And what they had been doing, these were two completely separate steps. And in fact, in some cases, they ran them on completely separate machines. So they would take the data, they would move it into step number one, they would do all the computing, and they would move it back. And then in serial process, they would then run the visualization, and they would move the data another time, and they would run the visualization process and move it back and then view it. So Dawei realized he had complete control over how the GPUs and how the CPUs interacted with each other. And so what he did was he took a handful of the GPUs. In this case, we still kept the same model. So these could have, and today, these probably would now be visualization GPUs. You know, this could be A100s over here, for example, and these could be, you know, RTX family. In his case, he was still using, you know, the same GPUs, but he took the data, he moved it to step number one to do the compute. And instead of moving it back and running it separately, the output of the compute was fed directly into the visualization GPUs. And, you know, the results were really dramatic because it cut the time for him to do the entire workflow, which is really what mattered. He cut it in half. And a side benefit that he has noted is that most other applications that were running actually improved in performance because he reduced the network traffic, because he stopped moving the network, the data back and forth so many times. And so, you know, he made the comment, instead of worrying about data offloads and so on, just don't move the data as often. So in summary, you know, IT is being asked to do a lot more work than they've ever had to do. They're supporting really dramatically expanding workloads, a diversifying architecture in terms of acceleration and storage. And oh, by the way, they're being asked to do it on the same budget. And as we've seen, each of the workloads, they're lumpy in their own ways. And so it's not just a matter of putting together an infrastructure with a bunch of different resources, right? You need to be able to optimize these architectures and ideally let the workflow determine the infrastructure as opposed to forcing the workflow to deal with the architecture that you've got. And so we really do believe then that fabrics as a universal dynamic fabric really lets IT do this. So it enables you to improve the system performance by adding in all of these new accelerator technologies. You can very easily revitalize existing infrastructure. You do not have to go out and do forklift upgrades on everything that's there. And therefore, it makes it much easier to meet budget requirements. And because you're getting better utilization out of the resources, you get better sustainability and better power usage. So with that, I am done. And we will open it up to questions that may have come in.
And thank you, Alan, for you and your team for the update today. And like I said, it's been a marathon, not a sprint for you guys. So congratulations on all the projects and or progress and where you've been able to get to with the technology. And we look forward to hearing from you guys again and doing more with you.